Hello, N4H&H here. This video is about power spectral density, but before we get into that, I want to go on the band here and let you listen to something. This is going to factor into the subject of the video. We're looking right now at my 32-inch Samsung monitor that is displaying the screen of the FTDX10. I'm using the FTDX10 primarily because of this the graphic that it has up there in the upper right. So let's listen a minute. There's a weak station out there. Enabling digital noise reduction. And narrowing the width. You can see that in the graphic up there. And engaging contour. So now that we've got the stronger station, I'm going to undo all that. And we've got this station is coming in at S3. Now I'm lowering the bandwidth, and look what happens. Or listen what happens. Going back to 3,000 wide, 3 kilohertz. And again, there's the weak station again, so I'm going to go back to contour, digital noise reduction, and a 2400 hertz bandwidth.
Yeah, that's why I said you might put you a 50 ohm on a real good one.
Okay, so now 3,000 hertz bandwidth, no contour, no digital noise reduction. Listen to his voice and the amount of noise.
He'll hand make you one. Tell him the problem you have, and he'll hand make you one, and it will promptly eliminate that issue. This SWR is not the only thing that amplifier sees, and you need to decouple it.
You notice his voice gets thinner sounding, but the background noise is going to be subdued. Compared to listening at 3,000 hertz, okay? So that's what I wanted you to hear from that is if I go narrow with my bandwidth, it improves my signal to noise ratio. Okay, now so armed and dangerous with that information, we're gonna move over to my my iPad here, and I've got something for you to look at there. Let me turn this down. Okay, so we have the iPad in focus now, and what I want to talk to you about today is power spectral density, or PSD, is the abbreviation. And if you've never heard of that, well, there's much information available about it, but I'm going to try to simplify it as it applies to ham radio, amateur radio, because it plays a major role in the digital world. And I don't just mean digital as in amateur radio, commercial digital as well. But I'm going to relate this to amateur radio and try to break this down so it makes sense. And the reason for this video is I've had some people comment, not just on my own YouTube channel, but I've read comments and heard of comments on social media about justifications for why they want to run wide transmit audio. And well, I say they didn't really even get into why. They just said they want wide. I even had a request, though I have no control over Yaesu, but someone asked, well, will Yaesu do any type of firmware update that will allow the FTDX10, for example, to transmit at 4 kilohertz? So I want to talk about that. Why would you want to do that? Well, for one thing, people are looking these days, it seems, with all the equalizers that are available, they want to sound like a broadcast station. Well, there is a trade-off for trying to do that. I am in agreement with the camp that says, look, 3 kilohertz of bandwidth is plenty for amateur radio. The human voice occupies 300 to 3,000 hertz, average person now. That can vary, if you're one of those, bass singers from a quartet, then yes, you may go down below 300 hertz. But typically, the human voice occupies the frequency spectrum of 300 to 3,000 hertz. So transmitting much broader than that is not really that necessary. You're gonna start transmitting overtones and even subharmonics, and there's a reason why that may or may not be a good idea. Again, it depends on what you're going for. But I am going for intelligibility. It's two-way communications. I want to get my signal through. And so this is where power spectral density comes into play. So let's get right in. Let's say that you have a 100 watt transmitter and you're running a 3,000 hertz bandwidth. Now, where that comes into play is in our radios, we have a setting in there, TX BPF, transmit bandpass filter. And, a lot of radios will offer a 100 to 2900. That's a very common width. And that is, if you do the math on that, that is a 2.8 kilohertz or 2800 hertz bandwidth. That's pretty full. But you may see options to run a complete 3,000 hertz bandwidth or even a 100 to 3,000, which is available in the Yaesu FTDX10, for example, just using it as an example because I've been shooting a series about it. So this is determining how wide your audio spectrum is going to be on transmit. So here's where power spectral density comes into play. If you're transmitting 100 watts sideband at 3,000 hertz or 3 kilohertz bandwidth, we do the math, we divide the power by the bandwidth, and we get an answer, and that answer is going to give us the watts per hertz. So at 100 watts, 3,000 hertz bandwidth, you're transmitting a power level of 0.033 watts per hertz. Now, let's say we narrowed our transmit bandwidth to this one here, 100-2900. So we're 2.8 kilohertz or 2800 hertz bandwidth. We've now increased our watts per hertz to 0.035. 3.3 versus 3.5. Now let's say I'm going to skip 2600, which is another option in there. I'm going to go straight all the way down to 2400. And if we divide 100 watts by 2400 hertz bandwidth, we are at 0.041 watts per hertz. So now I'm just going to factor in an amplifier. Let's say that you turn on a 1000 watt amplifier. That's a 10 dB increase in power, plus 10 dB. Well, you can see how that's going to work out. We're just moving the decimal one place to the right. The 1,000 watts divided by 3,000 hertz is 0.33 watts per hertz. 1,000 divided by 2,800 is 0.35 watts per hertz. That is a 5. And then 1,000 watts divided by 2,400 hertz is 0.41 watts per hertz. So you're getting a little bit more power per hertz in the audio spectrum by running a little bit more narrow, okay? Or even much more narrow if you want to consider, the 2,400 hertz. Now, before I get off this page, there's another page I want to go to, but I just wanted to mention, just as a refresher, if you haven't watched my video about decibels and S meters, one S unit is 6 dB change in volume, okay? It just means that it takes 6 decibels of audio increase or decrease for your ear to notice it. And that's why the S meter scale is supposed to be 6 decibels per S unit. We all know, and I did a video about it, that S meters are not all accurate. But that's the importance of the S unit, how it factors in, a 6 decibel change in volume would equal 1 S unit, and your ear can hear that. So up here, when we go from the 100 watts to the 1000 watts, we've increased by 10 dB. So clearly, that should show up on somebody's S meter. If their S meter were accurate, it would be factor in as almost a 2 S unit increase. So, but think about that. It takes a factor of 10 to gain that, 1.5-ish S unit. So let's put all of this in perspective. You've probably heard when you're working DX, or maybe even just tuning around and you hear somebody chasing DX, that their audio, some of the chasers, their audio sounds very thin or pinchy, almost like a telephone. Well, actually, that's intentional. The DX chasers will narrow their bandwidth to increase their watts per hertz. So, for example, if you go into your radio and you see that there's an option in your TX BPF, transmit bandpass filter, for 400 to 2600 hertz, that's 2.2 kilohertz of bandwidth, 2200 hertz. So let's do the math on that. It's so we're going to take 100 watts, divide that by 2200 hertz, and that equals 0.045 and 45 again, by the way. So now if we go back and compare that to the 2400 hertz was 0.041. So they are literally squeezing every amount they can get as far as the watts per hertz. Let me move that over a little bit so you can see as I'm cutting off a little bit. So 100 watts divided by 2200 hertz, 0.045. So they're focusing all of their power into a 2.2 kilohertz bandwidth. Now, yeah, we can all agree that's thin, pinchy sounding, but in that condition where they're trying to chase rare DX, you do what you need to do, and it's a smart move. Now, I think there's a happy medium. What you saw in the beginning of this video, those stations we were listening to at 3000 hertz bandwidth, by just us, not them, by us narrowing our bandwidth, we knocked some of that noise down and we're able to hear them with more clarity. So, hold on to that thought. Think about this. So SSB improves the watts per hertz because all the power is concentrated into one sideband, no carrier either. So if you think about that, the old 4-watt CB radio, right? That was the AM output, 4 watts. But you could buy a CB radio, you can today, that will do single sideband, lower sideband and upper sideband. And in those modes, the CB radios put out 12 watts. So think about that. We're taking away one sideband, we're taking away one carrier, we're concentrating all of the power the final has into just one sideband. And they share, whether it be AM, upper side, lower side, they all share the same final transistor. So you can see how it's more efficient when we're focusing all of our power into one sideband. So now on the transmitter side, and that's the transmit side. So if the person on the transmitter side were to narrow their bandwidth, again, 2.2 is extreme, but honestly, 2.8 is plenty. 2.4 to 2.6 is not a bad place to land if you're wanting to have the best compromise between how you sound, and still have some punch, not sound too thin, but yet take advantage of the watts per hertz, the power spectral density. So you're finding a compromise, and for me that compromise is somewhere in that 2.6 to 2.8 kilohertz range. Really 2.6 is going to probably be the best happy medium there. So, but 2.4 is not bad either. Now, and here's the key. If the person on the other end is transmitting at, say, a 2.4, and on your end you widen your filter to 3, you're just pulling in noise for no good reason. There's no reason for you to run more than a 2.4 bandwidth on receive, 2.4 kilohertz bandwidth on receive, if the transmitting station's transmitting at 2.4. So you see what I mean? And you can, by the way, you can tell if somebody's, first of all, they'll sound a little bit thin anyway, and then if you I should say thin. I shouldn't say thin. They'll sound thinner than somebody transmitting at, say 3K bandwidth. But you can widen your receive filter, your bandwidth, to 3,000, and you really won't notice any difference, any perceptible difference really, because they're already narrowed. They've already narrowed on the transmit side. So, in other words, ideally, if you know what the other person's bandwidth is, then you can narrow your receive bandwidth and you'll improve your signal to noise ratio. Listening more narrow improves the signal to noise ratio. But it's even better if the station on the other end, the one that's transmitting, is also transmitting a little bit more narrow. So, just try to match whatever they are. I mean, you're not necessarily going to get on there in a QSO and say, hey, buddy, how wide are you transmitting? Now, some of the modern radios today, including the FTDX10 and the FTDX 101D, the ICOM 7610, 7300s, they have scopes on there that do give you the ability to get to see how wide someone is transmitting. But just remember, listening more narrow improves the signal to noise ratio. Like I showed you in the beginning of the radio, we narrowed it down. We knocked the noise floor down some, but yet we heard them, and to my ear, we heard them with more clarity. So, final point on this, if you think about it, you probably, if you're not into CW, you wouldn't maybe know this, but CW, of course, CW operators know, CW is very efficient because of the watts per hertz ratio, and the receiving station can narrow their filter to improve the signal to noise ratio even more. See, with CW, we're just bursting a carrier on and off. And the receiving station, I've shown it in previous videos, I can narrow my bandwidth down to 50 hertz. And so, a super narrow bandwidth, therefore I'm blocking out, a plethora of noise. And I get down to where really, I can make them sound like they're a code practice oscillator. I remove all the noise and all I hear is the tone of the CW, which again, subject for another video, but I've talked about it in the past. They're not transmitting the tone. For those of you who aren't into CW yet, you're not actually transmitting a tone. They're creating the tone in their receiver, but that's a subject of another video. So the narrow bandwidth of CW is more efficient. So I hope this is a simplified explanation of power spectral density, but I wanted you to understand why it's not necessarily a good idea to run a wide transmit bandwidth, and much more than 2.8 kilohertz. Really is also not being very nice. We kind of have a gentleman's and ladies agreement on the bands to not exceed a 3 kilohertz bandwidth. That way, I can have a conversation on 14.250 and someone else can be having a QSO on 14.253, and yet another person could be having a QSO at 14.247. So when we try to widen our transmit beyond 3 kilohertz, we're not being very nice operators. But also, too, just remember that the wider we go like that, we're actually lowering our watts per hertz, our power spectral density, PSD. It's easier to say PSD, right? So I just want to get that out there as an explanation, especially for those who may be new to the hobby and wondering, what are these settings in my radio, TX, BPF, and such as that? You maybe saw in my FT991 video for Joel's voice, because that's his radio, my friend Joel, we ran the 300 to 2700 bandwidth, just 300 to 2700. So for him, 2.4 kilohertz, he wanted the punch. He's using the radio at 100 watts from his cabin. He doesn't have an amplifier. He wanted that extra punch. And but it also doesn't sound bad for conversation with him. Now, we did boost 300 hertz a little bit to, give it a little bit of emphasis on the bottom end, but we didn't run him any wider than, the 300 to 2700 hertz bandpass filter. So that's why I'm saying, just understand what we're talking about here when we talk about power spectral density, or if you ever hear that term, it really works in your favor to not try to run too wide. Okay, I hope that made sense, and I hope you found this video helpful and informative. I want to shout out to Mike there, who became a Patreon in the last couple weeks, and I failed to get his name out there. And thank you to the other Patreons who helped me continue this mission. And if anyone else would like to become a Patreon, please do. Your support is much appreciated. Go to www.patreon.com/N4HNH, patreon.com/N4HNH. And if you'll click the like button, subscribe to the channel, those help. And click the bell and you'll be informed when I upload the next video. Okay, well, I hope you have a lot of fun on the bands. Cycle 25 is beginning, and we should start seeing better propagation. I know it's not been great lately, but just keep hanging in there. And hey, thanks for watching. And this is N4HNH saying 73.